Most modern generative AI architectures evaluate logical truth by measuring similarity. They assume that if two statements map closely in a dense mathematical space, they agree with one another. When that assumption breaks, the entire reasoning structure destabilizes. Systems built on standard L2 norm or cosine similarity use symmetric distance metrics to judge meaning. In these spaces, words and phrases that share exact contexts often occupy the same geometric neighborhood, regardless of their actual logical relationship. Take a baseline medical evaluation. The phrase, "the patient has pneumonia," and the phrase, "the patient does not have pneumonia," are mathematically proximate in almost every standard embedding space. They share the same clinical vocabulary, yet logically they are exact opposites. Logical entailment is directed and asymmetric. A broad premise like "every poodle is a dog" logically supports the narrower conclusion "some poodles are dogs," but that relationship does not work in reverse. A symmetric distance model cannot encode this directed one-way subsumption. To evaluate logic, we have to look to topological deep learning. Specifically, we replace standard flat embeddings with a structure known as a cellular sheaf. Verifying AI outputs requires a shift in how we treat semantics. We have to stop executing simple proximity searches and start treating language as a directed constraint satisfaction problem. This animated network diagram shows the mathematical operator driving standard graph neural networks. This equation is the unnormalized graph Laplacian. This quadratic form looks at adjacent nodes, labeled here as U and V. It acts to minimize the raw numerical difference between those connected points. When we apply heat equation diffusion through this network, the operator smooths the signal. It forces connected nodes to share identical feature vectors. Enforcing equality across neighbors is a useful bias for identifying broad communities, but it fails when applied to logical rules. Contradictions, unit conversions, and temporal updates do not require things to be equal. In a logical graph, connected nodes often hold distinctly different vector values. Their relationship is defined by edge-specific rules, like transforming a measurement from Celsius to Fahrenheit, or updating an observation from yesterday to today. Standard graph neural networks enforce equality. Robust semantic networks must enforce mathematical compatibility. This diagram demonstrates a cellular sheaf. A sheaf is a graph that attaches independent vector spaces directly to its geometry. We call the space hovering above each node a stalk. The stalk holds the local semantic payload for that specific node. This can be a text embedding, a probability distribution, or strictly typed data. Between these nodes, we introduce the edge stalk. This is an entirely separate vector space placed directly over the connections. It acts as the arena where the two nodes will actually be compared. To move data into that arena, we use a restriction map. This is a linear projection matrix that connects a node stalk to an edge stalk. The restriction map dictates exactly which fraction of a premise's data is visible to the hypothesis it connects to. It filters out irrelevant dimensions and passes only what matters for that specific logical check. These maps natively handle asymmetric relationships. They project complex, multidimensional data from a dense premise down into a simpler canonical space, so it can be accurately compared to a specific hypothesis. By utilizing this structure, sheaves separate a network's topology, which nodes are related, from its geometry, the mathematical rules governing how those nodes interact. To see how this component-specific extraction works in practice, we can build a localized, four-node fact-checking scenario. This diagram shows four interconnected claims. Node A states, adults with type 2 diabetes. Node B states, the study had diabetes. Node C states, the study was pediatric. Node D states, children with type 2 diabetes. Each node stalk is partitioned into three distinct subspaces: age, condition, and population. Trace the restriction map from node A to node B. The premise in A entails the hypothesis in B by abstraction. The map only projects data from the condition subspace to verify diabetes, ignoring the age subspace. Now trace the restriction map connecting node A to node D. This relation checks both condition and age, so the map projects both of those subspaces into the edge stalk for comparison. Inside node D's edge stalk, a mathematical collision occurs. The vector representing adult from node A is mapped against the vector for child from node D. This collision generates a high localized error residual. The system isolates this error specifically to the age component, while confirming that the condition component is supported. A flat embedding model averages these components together. It finds the medical terminology topically close and returns a high similarity score, missing the precise contradiction. True semantic support is component-wise. Using generalized similarity scores to evaluate precise logical claims leaves critical applications vulnerable to hidden errors. To optimize this logic across a neural network, we use a single mathematical operator that aggregates all local restriction map comparisons. This equation is the Sheaf Laplacian energy. Instead of penalizing the raw difference between adjacent nodes, this equation penalizes the failure of transformed projections to align inside the edge stalks. It also includes a reliability weight, designated as WE. This weight allows the system to prioritize hard ontological constraints, like explicit database rules, over soft probabilistic guesses generated by a language model. The goal of this operator is to find the global section. In discrete Hodge theory, the global section is the state where the energy output equals 0. Reaching this zero energy state means that all local facts have been glued into a globally coherent truth structure. Every restriction map is satisfied. Under this framework, we treat hallucination as a quantifiable, differentiable failure of geometric gluing. This complex graph visualization represents how we scale the mathematics from a 4-node example to a massive retrieval architecture containing hundreds of retrieved documents and generated tokens. With some nodes known and others blank, the system executes harmonic extension. This is the computational process of solving for those unobserved nodes to minimize the total sheaf energy across the entire network. The retrieved source documents act as hard boundary constraints. They are locked values anchored to reality that the model cannot alter. The system runs a relation-aware diffusion process cascading across the graph. It calculates the exact mathematical values required for the blank-generated nodes to remain logically compliant with the hard evidence. If a conclusion requires an unstated premise to make sense, this diffusion process naturally infers and fills in the missing intermediate multi-hop proof steps to bridge the gap. Generating a truthful answer is identical to solving a continuous relation-aware semantic propagation problem. This matrix view shows spectral diagnostics. By analyzing the low spectrum of eigenvalues within the Sheaf Laplacian matrix, engineers gain an entirely new tool for structural safety. Small non-zero eigenvalues point to near-compatible modes. They flag areas of the network that are internally consistent but weakly supported, identifying hidden ambiguities or fragile assumptions within the language model's reasoning trace. Tracking this spectrum over time allows operators to isolate exactly where a global semantic collapse originated, pinpointing the single retrieved document that broke the logical chain. Early artificial intelligence relied on brittle symbolic logic trees. Modern neural networks replace them with statistical similarity, trading logical rigor for massive scale. Topological cell complexes provide the mathematical bridge to have both. To eliminate hallucinations and verify outputs, the industry must move past measuring the distance between words and start calculating the global consistency of semantic claims.